On this video, we will be showing how to get the electron configurations for cations or positive ions, as well as negative ions or anions. Before we start, I do want to point out that I did have a typo when I was showing you the energy level electron configuration. We've been doing the Aufbau, where you put everything in order of Aufbau's order of filling. But right here is where you put, some people will want you, some teachers may want you to do them by energy level, where you put all the ones together, all the second level, all the sublevels on the second level together, all the sublevels on the third level together, all the sublevels on the fourth level together. And I accidentally had a typo right in there. That was my mistake, so be sure you check your notes to make sure you have that correct. Let's move on. We are doing cation first. Bismuth, 83. First thing, always find it on the periodic table. Bismuth is right here, 83. And above bismuth, we have the little guide showing you what should be on the final level you're filling. Now, when we do an ion, whether it's a cation, which is a positive ion, or an anion, which is a negative ion, we do want to do the entire regular electron configuration first and then fix it by adding electrons for negative ions or removing electrons for positive ions. So this is my little guide. This is what I should be finishing with. And it should be finishing with an S2, F14, D10, and it looks like P3 as bismuth's the third one over. But what S2, F14, D10, P3 is it? Well, I just go straight over here. What is the S on bismuth's row? It's the 6S. So bismuth should end in 6S2. So I like to put where I'm supposed to go, what I'm supposed to end with. I like to go ahead and get it down right away, just so as I'm doing the rest of the inside, the beginning part of the electron configuration, I already know what the ending answer is supposed to be. So after that, we've got the 6S2, but it says 4F14 next. But what F? Well, if you just backtrack from bismuth, 83, 82, 81, 80, 79, 78, 77, 76, 75, 74, 73, 72, I'm looking at the atomic numbers, and then there's a red stop sign. And that stop sign's taking me right down here. Before 72 is 71, 70, 69, 68, 67. What is this? These are 14 elements in the 4F. So all you do to find out what you're missing on the inside is I'm just backtracking, making my way back to the starting line. I get to 72. We don't go from 72 to 57. I'm missing something between 72 and 57. What am I missing between 72 and 57? The answer is 71 to 58. That's the 4F. There are 14 elements in the 4F. So I'm going to come right here, and I'm missing 4F14. So after typing the 4F14, I come back. Yep, right above bismuth, it's S2F14. Where's the D? Which D is this? There's the D. Before I get the bismuth, I have to fill the 5D. There it is, 5D. How many elements are in the 5D? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements are in the 5D. So I know that this thing is going to end in 5D10, so I type it. S2F14D10, that is the same thing that we see right above bismuth, S2F14D10. P3, that is because bismuth is the third element over in the 6P. So which P3 is it? It's the 6P3. So I return to my drawing right here, my electron configuration, and I'm going to type in 6P3. So if I do bismuth's electron configuration correctly, this is what I should end in. 6S2, 4F14, 5D10, 6P3. But to do bismuth, to get the number 83, I go to the very beginning, and I'm just going to fill in everything. This is the electrons on the level that bismuth is being filled. This is the outer part. I want to fill the inside, everything that's not on that level. And we call all that inside stuff the kernel. That's the inside. All the electrons that are not on that outer part of the element. So I got to go back. How do I fill in this for bismuth? There's bismuth, 83. I've got to start at square one hydrogen, and I'm just going to work my way through all of these levels until I get the bismuth. So I'm going to start with the number 1 and 2. That is in the 1s. That is the S block. That is the 1s, and there's 2 elements there. So I type 1s2. Then I head back in. After number 2 comes number 3. 3 and 4 are in the 2s. So there's 2 elements in the 2s, 2s2. I head back and I'm going to type in 2s2. As you can see, electron configurations are a little easier to do than the orbital notations where we had to put in all the arrows. Electron configurations are just orbital notations without the arrows, boxes, lines, and numbers above the boxes. It's just giving us what was underneath it. So after the 2s, where do I head to? I just finished the 2s, number 3 and 4. 5 through 10 is the 2p. How many elements are there? 6. So I'm going to come back here and type in 2p6. After typing in the 2p6, I'm going to come back here. I'm right there. That's the 2p. After number 10 is 11 and 12. I'm just following the numbers. 11 and 12 are in the 3s. How many elements? 2. So it'll be 3s2. After typing 3s2, I bounce back out here. 11 and 12 are the 3s. 13 through 18 are in the 3p. How many elements is that? That is 6. So I return to my drawing and I'm going to type in 3p6. After typing into 3p6, I am now at argon 18. So I'm going to continue on into 19 and 20. That's 4s2. After typing 4s2, I'm going to return. What comes after the 4s? Well, we learned the 3d does, and we learned why. It's all energy. The energy of the 4s is 4. Why? Well, to get the energy of the sublevel and energy level, we add the n, that's the number in front, in this case 4, and we add the L. Well, 4s, the s is not a number. What is the number that corresponds with the s? It's 0. 4 plus 0 is 4. So the energy of the 4s is 4. The energy of the 3d, what's my n when I'm in the 3d? My n is right there. It's 3. What's my second number? When you're in the d, your second number is a 2. 3 plus 2 is 5. 5 is bigger than 4. Opal says fill the lower energy first. So now we're on the 3d. There are 10 elements there. So it's 3d10. After typing 3d10, I return to the table. After number 30 is 31. 31 through 36 is the 4p. So I type 4p right on my electron configuration. After typing 4p6, I return again to the periodic table of elements. After number 36 is 37 and 38. That's the 5s. There's 2 elements in the 5s. So I'm going to come back over here and type in 5s2. After typing 5s2, I'm going to return to the periodic table. I'm right here, 5s2. After number 38 is 39. 39 through 48 is the 4d. Remember, these are n minus 1. So if this is 5, 5 minus 1 is 4. I really don't need this even typed in there for me. I can figure it out by just knowing these are n minus 1s. And the F block down here is n minus 2s. So here we go. There's 10 elements in the 4D. So I'm going to return and type in 4D10. After typing 4D10, I'm going to return to the periodic table. Here's the 4D10 right here. After number 48 is 49. And that's important that you watch these numbers. Because if you watch the atomic numbers and you're just following, we're trying to get to number 83. If you're following the numbers, it will guide you exactly when to bounce down here, as you'll see in a second. But after the 4D, after number 48, we come to 49 through 54. That is the 5p. You're like, how do I know? 5, and this is the p part of the table. It's the 5p. There is no n minus anything up here. The S and the P are the main blocks. The sublevels line up with the energy levels. 5p6. So I'm going to return here, and I'm going to type in 5p6. After typing in 5p6, I return to the periodic table. The 5p6 is right here. What comes after the number 54? 55 and 56. That is the 6s. How many elements are there? There are 2. 6s2. So I'm going to return. Now I don't have any more room here. So I'm just going to put the 6s2 right there. And now I'm going to return. We know what's supposed to be the rest of the way. Let's verify that it's 4f14, 5d10, 6p3. We return here. What comes after 56? The 5D opens. The 5D looks like it's next. Lanthanum actually will have one in the 5D. But after we go to 57, we can't go straight to 72. 57 to 72 is not, we're missing some numbers in there. When you realize there's a jump, and we see the red line right here, it's telling you stop, come on down, follow it over. After lanthanum, we go to this group right here. That is the 4F. I'm just following the numbers. Now, as it turns out, one electron does go into the D before they fill the F. But the F is the next sublevel filled, so that will go in the order. How many elements are there? There's 14. So I'm going to return here, and I'm going to write 4F14, as I did before I even started the problem. Now, how do I know where to go after that? We go back to the periodic table. I've got the 4F14. After 71 is 72. Where do I go after 72? There's 72 right there. That's telling you just return to that spot right there, and now we can fill the 5D. How many elements are there? Let's count them. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to return and make sure that I wrote 5D10. I did. Back to here. I am now in the 6P. 1, 2, 3. Bismuth is the third one over in the 6P. I'm pretty sure I have my configuration correct, but now I want to check total numbers of electrons. This is bismuth 83. I have not made it 3 plus yet. 2, 2 and 6 is 10, and 2 is 12, and 6 is 18, and 2 is 20, and 10 is 30, and 6 is 36, and 2 is 40, and 10 is 50, and 6, hold on. Try that again. 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 66, 70, 80, 83. Yes, I have the correct number of electrons, but I'm supposed to do bismuth 3 plus, so now it's time to remove electrons. Where do we remove them from? The valence. The valence. My valence is right here. There is a 6. There is a 6 right here. And there is a 6 right here. Those are my biggest numbers. That is my valence. There's 2 here and 3 there. So bismuth has 5 valence electrons. On the periodic table, we should see a Roman 5 above bismuth. There's bismuth. There's the Roman 5. So we remove the electrons from the valence. Here we go. I'm going to pull these 3 first. It's 3 plus. These are the 3 that get removed when we make bismuth 3 plus. You remove the electrons from the highest energy sublevel first, the outermost, the valence first, the 6p goes first. Now, if we needed to remove additional electrons, we would pull them out of the 6s, not the 4f or the 5d. We would pull them out of the 6s. Now, one last thing to look at. This took a lot of time to draw out this. As you can tell, chemists are a little bit on the lazy side. They would not want to draw all this out because all the action was happening right here. We're going to learn 2 more ways to do this. One of these is called noble gas notation, nearest noble gas notation, or compressed or condensed electron configurations. There we will learn how we can replace this with something else to speed this up significantly. Because the business end, when we're making ions and so forth, we're looking here. Now, did bismuth, losing those 3 electrons, leave bismuth with the stable octet? And the answer is no. The 6s still has electrons in it, 2 of them. If bismuth could lose those 2, then bismuth would be left stable, because it would have 6 in the 5p, 2 in the 5s, 2 and 6 is 8. That's the octet rule. Having 2 here, you're like, well, what about the duet rule? If it loses those, the duet rule is satisfied. No, no, no. The duet rule only applies to hydrogen, helium, lithium, and beryllium. We will do our final ion in the next video, the fluoride ion.